with a new problem from theory of estimation, that is show that S square is a biased estimator of sigma square. Also we need to find out the unbiased estimator of sigma square. This is a very important question from your examination point of view, and we will going to solve it with a very easy approach. Okay, so let us start the solution with some basic assumptions and some basic understanding of the theory. So first of all, in the last video we have gone through what is biased estimator and what is unbiased estimator. I will going to recapitulate once again about it. For example, if we are having Tn is the sample statistic of the sample observations x1, x2, x3, xn, which is taken from normal distribution with mean mu and variance sigma square. Then it is very clear and is evident that x bar, what is x bar? X bar is the mean of the sample means of these observations. They will follow a normal distribution with mean mu but variance of sigma square by m. That we will see once again. What is this Tn? Tn is the parametric observation of the parametric function of the sample observations. Okay? And how do we define unbiasedness? We define unbiasedness as if E of Tn is equal to theta. What is theta? Theta is the population parameter. Tn is the parametric function of the sample observations. Then we can say that Tn is an unbiased estimator. Tn is an unbiased estimator of theta. So in the last video we have gone through this theory. But what is biasness? Let us see this. What do you understand by biasness? If E of Tn is not equals to theta, then if E of Tn is not equals to theta, then we can say that Tn is a biased estimator. Tn is a biased estimator of theta. Tn is a biased estimator of theta. And what is the measure of biasness? What is the measure of biasness? The measure of biasness is E of Tn minus theta. Sorry. E of Tn minus theta. This is called the measure of biasness. Measure of biasness. This is the measure of biasness. Now from this theory we will going to proceed to prove this statement, that is S square is a biased estimator of sigma square. Now let us move to the S square part. What do you understand by S square? S square is the sample variance. Okay, S square is a sample variance, that is the variance that we are getting from our sample observations when we are calculating that. So S square is defined as summation I is equal to 1 to n xi minus x bar whole square by n, where this n is the number of sample observations. Okay, the number of samples we have taken. This is my S square. And what is sigma square? What is sigma square? This is my population variance. This is my population variance. Okay, which is fixed but which is unknown. Which is fixed but which is unknown. So basically, what we want to do? We want to take the sample. We will be calculating the S square, that is the sample variance, and then we will going to estimate the value of sigma square. Okay. Now, what result that we have shown in the last video is that E of xi, E of x bar is equal to mu. This was the proof that we have done in the last video. Okay, E of x bar is equal to mu. So we have seen that this x bar is a unbiased estimator of mu. Now, as per the statement, it is very clear that ESS square should not be equals to sigma square, and this we need to prove. So what we need to prove? We need to prove that ESS square is not equal to sigma square. Okay, so let us start with from the beginning of the expression. So let us start from the beginning with the expression E of S square. What is E of S square? E of S square, we can write E of summation I is equal to 1 to n xi minus x bar whole square divided by n. So 1 by n is a constant term, we can take it outside expectation. So we will get here 1 by n E of summation I is equal to 1 to n xi minus x bar whole square. If we expand this term, then we will be getting 1 by n E of I is equal to 1 to n xi square minus 2 xi into x bar plus x bar whole square. This is the expression that I am getting. Okay, now let us count this time. From here we will be moving to this side. So now I can write here E summation of xi square by n. This 1 by n I am taking inside the bracket. So summation xi square by n minus 2 you can write like this, summation xi by n into x bar. This x by xi, summation of xi by n into x bar. Okay, and here you have to put the summation as well. Okay, so these are the summations. So this is summation xi by n into x bar plus summation of x bar square. Summation of x bar square. Simply what we have done, we have taken this 1 by n inside, and this summation, is already there. We are just expanding the terms. So here we will be getting E. Now this xi square, if I count sum the values from 1 to n, this will be this will be xi square by n minus this one, summation of xi by n. This is the definition of x bar, right? So we can write here 2x bar square, because already there is 1 x bar into another x bar, so we are getting minus 2x bar square plus oh, I missed out one. This n should be here because I am dividing all these terms by 1 by n. Now this is summation of x bar square, so this is a constant term and I am adding it up to n times, so this will be n into x bar square divided by n. Okay, n into x bar square divided by n. So what I am getting here, E into summation of xi square by n minus 2x bar square, this n will cancel, plus x bar square. So ultimately what I am getting, E of summation of xi square by n minus of x bar square. Right? So if we now apply the property of expectation, I will get here E summation of xi square by n minus E x bar square. So this will be my first equation. Okay, so E summation of xi square by n minus E of x bar square. Okay, so let's proceed for the next step. So here this equation, so equation 1 can be written as summation of E xi square by n minus E of x bar square. Right? So equation 1 is written in this format. Now again, if we go back to definition of expectation, we know that variance of xi, this is the definition of the variance in terms of expectation. We get that variance of xi is equal to E of xi square minus E of xi square minus E of xi whole square. This is by definition what we are getting. We know that variance of xi is written as sigma square. This exi square will be there minus this E of xi by definition is nothing but mu square. Okay, so therefore E of xi square, if we take mu square in the left hand side, I will get sigma square plus mu square. So this is my equation 2. Okay, now if we put equation 2 in equation 1. Okay, what is the equation 1? The equation 1 is 1 by n summation of E of xi minus E of x bar square. So this will be equals to 1 by n. Now here what I will write, summation of from equation 2 sigma square plus mu square minus E of x bar square. Now again this sigma square plus mu square is a fixed quantity and we are adding it up to n times. Therefore I can write here 1 by n into n sigma square plus mu square minus E of x bar square. Okay, so this n will cancel and ultimately I am getting here sigma square plus mu square minus E of x bar square. So this is my equation 3. This is my equation 3. So just I am putting the value from definition. We know that variance xi is this. So just I am putting the value over here and then I am finding exi square. So I am just replacing the expression of exi square by sigma square plus mu square. I am just replacing this in equation 1 and I am ultimately getting this value. This is nothing but my equation 3. Now from the property of variance, we know that if the variance is written like this, what is this? This is variance of some term multiplied by a fixed quantity, and if we want to take the fixed quantity outside the variance expression, then it will be squared up. Variance of xi. This will be written like this. This is the property of variance. Just to recapitulate. Now, if we write, say, variance of x bar. What is x bar? X bar is variance of summation of xi by n. Okay, I am just replacing the expression of x bar. What is x bar? By definition, it is summation of xi by n, and this n is a constant term. 1 by n is a constant term. It will be taken outside. Right? If it is taken outside, then I can write this as 1 by n square variance of summation xi. This I can take. If I take this summation outside, then this will be 1 by n square summation of variance xi. Okay? Now variance xi is nothing but sigma square, and if you add sigma square n times, this will be n into sigma square. So ultimately I am getting 1 by n square into n into sigma square. So this will cancel out and ultimately I am getting sigma square by n. This is a very, very important derivation. Okay? That if x1 to xn is a sample unit which is being taken from normal population with mean mu and variance sigma square, then the mean of the sample distribution will going to follow a normal distribution with mean mu and variance sigma square by n. This property I am going to use for the final part of my proof. Okay. So now let's move to the equation 3. We know that variance of x bar, this is again by definition, variance of x bar is equal to E of x bar square minus E of x bar whole square. This is again by definition. Now already we have proved that variance of x bar is nothing but sigma square by n. This will be E of x bar square minus E of x bar means mu. In the last video we have already proved this, right? Because x bar is an unbiased estimator of mu. Therefore, we can replace this E of x bar whole square by mu square. Therefore, E of x bar square is equal to sigma square by n plus mu square. This is my equation 4. This is my equation 4. Okay. Now what I will do, I will replace the value of E x bar square from equation 4. So let us do that. So you write down here sigma square plus mu square minus sigma square by n plus mu square. You write here from equation 4. Therefore, sigma square plus mu square minus sigma square by n minus mu square. And what is this? This is your E of s square. So friends, here what we can do, we will going to cancel this sigma square out, and ultimately we will be getting sigma square minus sigma square by n. So this is, if you take sigma square common, this will be 1 minus 1 by n. Okay? So if we simplify this, it will become n minus 1 by n into sigma square. Now you can see, we have started from ESS square and we have proved that it is nothing but n minus 1 by n sigma square. So we can say that this is ESS square is not equal to sigma square. So if we label it as equation 5, then from equation 5, E of s square is not equal to sigma square. E of s square is not equal to sigma square. Why? Because E of s square is n minus 1 by n into sigma square. So the first part is proved. What is the first part? Show that s square is a biased estimator of sigma square. So since s square, E of s square is not equal to sigma square, therefore s square is a biased estimator of sigma square. This is the first part of your proof. Now we are coming to the second part. Okay, so also find the unbiased estimator of sigma square. So if s square is not an unbiased estimator, then what will be the unbiased estimator? So suppose we have got the sample variance, how we will going to estimate the population variance now. So from equation 5, ESS square is not equal to sigma square, that is fine. But what is ESS square? ESS square is n minus 1 by n into sigma square. So if you multiply this n minus 1 by n factor over here, then this will be n by n minus 1 E of s square is equals to sigma square. Okay, this is equals to sigma square. Now if we take this n by n minus 1 inside, then we will be getting E of n by n minus 1, and we replace this s square by its expanded form. Then we can write this as summation xi minus x bar whole square by n, because we know this is the definition of s square, is equal to sigma square. We know this is the definition of s square. So now we will going to cancel this n, and ultimately we will be getting expectation of summation xi minus x bar whole square by n minus 1 is equal to sigma square. So this expression, the expectation of this expression is nothing but is equal to sigma square. So we can say that this is an unbiased estimator of sigma square. Okay, so if we replace this value by capital S square, then if we replace this value by capital S square, then we will be getting E of capital S square is equal to sigma square. So friends, here small s square is not an unbiased estimator of sigma square, but capital S square is an unbiased estimator of sigma square. So whenever we will going to estimate the value of sigma square from the sample, we will going to use the denominator as n minus 1 and not n, right? So we can say where s square is equal to summation of xi minus x bar whole square by n minus 1, right? So s square is the unbiased estimator of sigma square. So this particular problem is solved from here. Okay, so if we summarize it, it's very simple. What is estimator? When we have a sample statistic, right, and we have to estimate the unknown population parameter, right? We cannot just say that whatever is the sample value will be exactly the value of the parameter. Okay, so what we need to do, we need to find out some of the estimator. What could be the good estimator? So one of the property of a good estimator of the population parameter is unbiasedness. There are other parameters also which we will going to take in the later videos. That is what is a consistent estimator, what is an efficient estimator, what is a sufficient estimator, what are the properties for that. That we will be coming with in our next videos. But here we have seen that what is unbiasedness, okay, and the two important parameters and two important statistics, that is the mean and variance. The mean is an unbiased estimator of population mean. The sample mean is an unbiased estimator of population mean, but sample variance is a biased estimator of population variance. Only if we divide the summation of xi minus x bar by n minus 1, then we can convert it or transform it into an unbiased estimator. Thank you so much. I hope you have understood this. In our next video, we will be coming up with a new chapter which is called testing of hypothesis. We will be doing 2-3 important sums that will come in your exam or may come in your exam, right? So until next time, thank you so much. And yes, don't forget to subscribe, like and share the videos, right? So that you can get information about it. Thank you so much.